Gosh, I'm never going to figure these strings out. This week we're going to revisit an old data type. So we're kind of going backwards in time, but as we're going to look at this week, not really. I've been kind of lying to you. Strings, as I promised in the first week of Python programming, which I think was week numbered 1, are a data type. But they're not like numbers and they're not like decimals, right? They basically contain things like, well, characters and the symbol representation of numbers, and as we'll find out this week, actually spaces. But they function actually more like a data structure than they do as a traditional data type. So I just told you that strings are data structures. Except, what do I do about that? In this video, we're going to use a magic trick. We're going to transmute the word gel into the word try. And what we're going to find out is, well, these are still words. They're composed of letters. But actually, they're a data structure that are composed of smaller pseudo-data structure called characters, which looks at each letter by letter in a list. Because insofar as our computer is concerned, it does not care what these are. And in fact, they actually correspond to numbers that live in a larger table that's part of every single computer. Then we're going to learn some functions that we can interact with, and we can learn how to change these strings using this principle. So the ASCII table, this ASCII table, stands for American Standard Codes for Information Interchange. And the reason why it exists is because computers don't actually know what letters are. However, what they can do is store them in a gigantic lookup table, the ASCII table, that allows us to type words. The computer will decode them to these numbers that will then allow us to shift, for example, the letter G to the letter T. So let's break down the word gel. As you can see on my screen, the letters are G, E, and L. And in the ASCII table, these exist at the following, what are called code points, or numbers in the ASCII table that the computer uses to understand where they sort of live in this space. We're going to use these numbers and do some math to move, for example, the G to the letter T, the E to the letter R, and the L to the letter Y. So what we're going to do is we're going to take the G, for example, turn it into its code point, add a number, get a new code point, and then bring it out of that into a letter character that we understand, rather than a series of numbers that are more accessible to your computer. And like I said, we're going to learn some functions such as ord, char, and look at some other properties of strings in order to understand how to do that. So we're familiar with strings, and we would understand that we could set up a thing called word, and it should get the value of GEL for gel. But there are a couple of things that we can do to this particular variable in order to understand it better as a list. And one of those things that we can do is we can use a function that we learned last week as part of our data structures week that allows us to look at the length of this particular word as a list. And if that works, we should just be able to print len of word and get a 3. We can visually verify that, but at the same time, we also know that we can ask any list for its len and get the answer, and in this case, it is in fact 3. Another thing that we can do that we knew about lists is we can ask for letters by index. And I could print for the 0th or first character of the word. I could look for word 0, or I could print, for example, word 2 to get the last letter. And I get a G and an L, just like I could do if this was in fact, and it is in fact, a list. The last thing I could do is I could say for letter in word, and I could print letter and get, just like for name and cat names, each individual entry in the list. All 3 of the indexes here. And so if I were to print that out, I get my G, E, and L, just like I did last week when I was looking at cat names. So what we can conclude from these examples is that string behaves a lot like a list because it essentially is a list. And each entry, each index, is a single character. So I've done some setup here. The first thing I've done is I've redefined word as gets the value of gel. I've created an empty list called changed word to store all of the values of the shifts that I'm going to do. And I've created a for loop that's going to loop letter by letter in order to allow me to affect the G, the E, and then the L. So the first thing I'm going to do is I'm going to create a shift that is the ordinal value of letter plus 13. That's my 13 place rotation. I'm pushing the letter 13 points down the ASCII table. The next thing that I'm going to do is I'm going to add to changed word. I'm going to append using the chur or chr function, which turns my ordinal values, my numbers, back into characters. So I've shifted them 13 places. They should be the T, R, and the Y. And I'm going to add the character value of shift, and I'm going to print changed word below, just to make sure that I've done it. And then I have T, R, and Y, which is an actual list. It is not a string quite. Strings behave a lot like lists, and in fact, they are lists, but they are a shorthand version of lists that allow us to read messages and to read symbols and characters as if they are just plain text. They're not all broken up like you see this list here. There is a way that we can rejoin this list to create a word out of it, and that's by using the join method of string, which works just a little bit differently than other methods that you might have seen. So I'm going to say transformed equals, and I'm going to use the method here, which is, again, used just a bit differently than you've seen methods, but not too much so. You have to use the glue or the thing that you want to join the letters together with, and I'm going to join them with a blank so there's nothing between them. And I'm going to say dot join, again, the join method of this string, and I'm going to say join changed word. And if I were to print transformed, I should get try. And at the end of that operation, I got exactly what I wanted, but I wanted to step back just a bit to highlight something specific about strings. In most programming languages, spaces are not nothing. They are actually characters in the ASCII table. For example, if I wanted to join each of my letters and I was thinking, oh, I want to join them by a little space between them, and that'll glue them together. No, we need to use those double quotes smashed together like we do with our break statements. But if I were to say transformed equals dot join changed word, and then print transformed, you'll notice I get T space R space Y. And that's because the space actually has an entry in the ASCII table. If I were to print the ordinal value of just a space, you'll notice that I get the number 32. And that's because it actually takes up space, right? Spaces are not nothing. Keep that in mind as you're working with strings. And that's just a short example to show you what strings really are. They're true selves. They're really just special data structures. And they're data structures that store those symbols, but really decode down to what are called code points in order for a computer to represent language. Because again, computer does not care what the letter C or the letter E or the letter J really are. And in fact, as we know, there are many more languages than just English in the world, and they have their own representations in something called the UTF-8 character set, which we're not going to talk about this week, but that's something you can keep as trivia in your back pocket. However, what we will see this week is that we will see that strings, just like lists, have special powers that allow us to do special things with them and make them much more useful in our programs. And we'll see those in the upcoming couple of videos.